Welcome to Inside AI, a podcast from the EPFL AI Center. I'm your host, Marcel Salathé, professor and co-director of the EPFL AI Center. Each episode brings you fascinating discussions with brilliant minds from EPFL and across the global AI community. From groundbreaking algorithms to ethical considerations, from technical innovations to real-world applications, we explore the technology that's transforming our world. Whether you're an AI researcher, industry professional, or simply curious about the technology that's shaping our future, join us as we venture inside AI. Today I'm speaking with Babak Falsafi. Babak is a professor of computer science at EPFL and an expert in computer architecture and digital platform design. He was previously a professor at Purdue and CMU, and he's also an IEEE fellow and an ACM fellow, among others. Now, Babak is the founder of EcoCloud, which is a center at EPFL, so similar to the AI Center, and its goal is to tackle issues related to sustainable computing. He's also the president of the Swiss Data Center Efficiency Association. All of this makes him an expert in sustainable cloud computing and sustainable data centers, which is why I wanted to talk to him. The question of energy demand for AI is one that's on many people's minds, and Babak is really the person to talk to here at EPFL about this. Though, as you will hear, it's important to distinguish between data centers, cloud computing, and supercomputers, a distinction I haven't always correctly made. So this was a very educational exchange, at least for me. I learned a lot, and I hope you will also enjoy the conversation. So here's Babak Falsafi. All right, Babak, thanks for coming on the podcast.
Thank you very much for having me.
So let's first help the audience get a sense of who you are. So one hat that you wear is you're the founder of EcoCloud, that we're reading a lot about these days for the reasons we will learn about later, because cloud, energy, and so on is all a huge topic. Can you tell us a little bit what EcoCloud actually is and what it does?
EcoCloud is an academic research center we put together at EPFL in 2011. A bunch of us came together. At that time, data centers were making the news. It was the beginning of the data deluge. Everybody's talking about data. There was nothing about AI at the time. And it was clear that data center growth was a huge concern, and the electricity consumption of data centers was a concern. At the same time, the foundational technologies that make that are in every little chip that we use today to compute, those follow an exponential trend called Moore's Law. It's token after one of Intel's co-founders who recently passed away. We doubled the density of chips every 2 years. With that came free electricity because each element also became more efficient. That was slowing down. Just like every exponential, these things also slow down. That took 5 decades. It's coming basically to a halt because of limits of physics. So those two things together, we saw data deluge, we saw post-Moore, and we said, okay, we need to worry about data centers. We found EcoCloud. A bunch of us came together. It was an industrial and academic consortium where we worked together with a number of companies to solve some of these problems.
But when you said we need to worry about data centers, which aspect in particular was sort of the...
Well, we saw the growth in data deluge, and data centers basically are a foundational pillar to store, collect, process, and eventually deliver data. And because of data deluge, we saw already a growth and interest in data centers.
Okay. You are also the president of the Swiss Data Center Efficiency Association. Tell us more about that. That sounds interesting.
Right. So SDA was founded a few years ago. There was a group, another industrial academic consortium, this time in Switzerland, came together. There was a challenge announced by Digital Switzerland. It's what are the challenges of digitalization? And they proposed, they responded to this challenge by bringing this group together to create a label that properly quantifies energy efficiency and emissions in the operation of data centers. That label, since now, has been launched, and we have a number of customers, not just in Switzerland, but now we recently also certified our first EU data center in Luxembourg. And it also comes with a navigator platform. There are 3 calculators. Customers can go and use the calculators to measure their efficiency if they want. One is for energy flow inside a data center. The other one is the IT stack, which is novel because it doesn't exist elsewhere. And then the third one is emissions, which is emissions due to a source of electricity. This nonprofit is also partially subsidized by the Federal Office of Energy in Switzerland.
Good. So we want to talk about cloud and AI and energy. So it seems like you're the right person to do this, given what you just said. So again, really appreciative of you being here. Maybe let's start just with a sort of general description of the situation so that people understand. I mean, I think there's a broad understanding out there that cloud needs energy. It's growing now. AI, right, adds to that. There might be a bit confusion about actually how much that is. And despite all the enthusiasm for AI, that seems to be a major concern. At least also when I speak to people, one of the key issues that comes up is the energy. Maybe it's a European phenomenon. You can tell me more later because you're traveling quite a bit internationally and talking to people elsewhere. But certainly here in Switzerland, and I think in Europe, energy and the sort of pollution that can come from energy production in the context of AI seems to be like a major issue. And we can go into the details in that conversation. But first, to sort of map it out, clearly cloud demand is growing. Can you give us a sense of like, what are we talking about? What are the orders of magnitude? How rapid are things? Which part is from AI? What do we even know?
Good question. So let's talk about the magnitude. First of all, the cloud is an economic model. The goal of the cloud is to centralize infrastructure and basically make it super economical to provide IT services globally. And that's successful. It's taken off for over a couple of decades now, and it will eventually basically consume all form of computing because it's the most economical way of offering IT services. Having said that, in 2024, the overall global data center investment was around basically $300 billion. Cloud revenue was at $700 billion. So somewhere between $300 billion and $700 billion.
That's per
profit.
Year.
That's for 1 year.
Yeah.
And now talk about electricity consumption. It's estimated to be growing at around 16% a year. Electricity consumption, this is an article that came out of Goldman Sachs. There was an article that came out this month out of International Energy Agency, 300-page document that also gives similar numbers. We have, if you look at a plot of electricity consumption data centers, it was pretty flat for a few decades. And the reason was that the data centers were getting consolidated and becoming bigger. The mom and pop machine rooms would go away, and it would create more efficient data centers because the data center operators that are also multinational, whether it's the hyperscalers or whether it's the co-locators in Europe, they also want to make profit out of that. So they'll run a more efficient data center site. So 2024, overall electricity consumption of all data centers globally was around 400 terawatt hours for 1 year. This is roughly half the electricity of Japan. If you grow at 16% a year, basically after 2030, we're already surpassing the electricity of Japan. We double that total electricity consumption. Out of that, what is expected is around, perhaps by 2030, not now, you would have anywhere between 20 to 25% of it being AI. Now that's just a projection. So most of the electricity is going to data centers. Data centers, by the way, also are the pillars that provide the cloud. That means all of the activity we have, which are IT services, are based on data centers. Data centers, on the one hand, deliver data to the customer through the cell phone. And on the other hand, they have an internal data customer, which is AI. And the part that where they're delivering directly to the customer is paying. That's the cloud. The part that's AI, it's still an investment.
Okay, but to maybe put that in context. So you're saying with the current projections, and they may be too low, they may be too high, but we're looking at AI being a quarter, maybe a third of that energy consumption in the cloud in 2030.
2030, yeah, past.
And today it's half of that. It's 10%.
It's little. It
little.
Show up on the map.
Because I think that's very important. I'm often reading articles, even in sort of well-established newspapers, that have somehow read that apparently it's already today 50%.
So the problem is that this first of all, the Goldman Sachs article is already, from the beginning of the year. Projections are extremely hard to come by. There's extremely little transparency in what's going on. The major providers don't want to be measured. The minute you expose any information about what is happening, that also will leak, their business model, they'll leak proprietary information. So they don't want to have anybody measuring anything. But there are decent projections that one could imagine. You sat down yourself and did a quick calculation. I did a similar calculation based on information that was available on the web. It sort of matches out, right? Yeah. One query is whatever 0.1 watt hour, one image is 2 watt hour. There is a series of articles coming out of MIT Technology Review now that says it's much, much bigger than that. The minute you do a quick announcement with a flyer and a little bit of a video, you're going at 1 kilowatt hour. That's just one flyer creation for the announcement of an event, including a video. So it's difficult to project.
Yeah.
Right.
If I understand you correctly, you say there's probably a case to be made that these projections may be on the conservative side. And given just how we see that now, image generation and video generation and agents and what have you are taking off, and they are just taking orders of magnitudes more energy than your random ChatGPT text-only request, that could actually become a serious issue in terms of energy needs.
Right. So there are two things, right? One is that OpenAI has given it away for free, or so is Google with Gemini. They're going to throttle that. Yeah. They're going to let you have as much free as they think is worth the data they're getting, right? Beyond that, you're going to pay. So that's one thing. The other thing is that these companies are the top 5 most valued companies in the world. 4 of them are these hyperscaler cloud providers. They're all after energy. There's no question about that. They've already announced that they're after energy. In fact, the rest of industry, especially in the US, I don't know what's going on in China, the rest of the industrial world is worried about this top 5 because they're powerful, they have money, they might also monopolize the energy markets. But there's no question about it. Microsoft has 2 central partnerships. One is with the 3 Mile Island, they've already announced. The other one is with fossil fuel companies because AI can help with energy extraction. The other ones have announced Amazon, Google, this modular nuclear technology, which makes no sense because the modules, if they actually work, they're 10 megawatts. 100 megawatt data center is the largest we have in Switzerland, and those are really small.
Yeah.
Right.
Okay, we can let's get to that a little later. We can dig into various aspects. One that I find really interesting is just to dig down a little bit and say, okay, what is actually the unit here that generates this demand for energy? I guess if we just sort of simplify it a little bit and let's just stick to the AI side of things, we're largely looking at GPUs, I assume, but correct me if I'm wrong. And there, right, if you would look a little bit at sort of the NVIDIA chips, because they're still sort of by and large, right, the dominant chip, the power for these machines has gone up considerably. In 2012, that used to be about 200 watts, right, per chip. Now the Hopper, which is sort of the standard chip at the moment, or at least has been in the last few years, is at 700 watt, and the next generation now that we're using, this Blackwell chip, is already at 1,200 watts per chip. So that's, give or take a 5-fold increase. At the same time, when you look at performance that you're getting there per watt, that has also gone up by about the same factor. So we have, the machines have more power, they deliver more by power. Somehow, at the same time, right, we would think, oh, that should somehow keep everything flat because, right, you're getting more powerful machines. They deliver more performance per power, but it just seems like people are buying more and more of these machines. Is that dynamic, you think, because you mentioned previously about, every exponential will eventually come to an end, but in those domains right now, it looks like it just continues to grow. You see that coming? Are we ever going to be in a moment where we say, okay, now we have enough power, enough sort of compute per power that actually we just get by with the next generation of chips? We just have to replace them because they will be so much powerful, so we don't need absolutely more.
So this is a very good question. So first of all, the improvements in efficiency at the chip level, NVIDIA's chips have gotten 8x more efficient in terms of operation per watt over 3 generations. Those 3 generations are not following the Moore's law because Moore's law was 2 years doubling in density, but over a larger time span, they've in 3 generations basically they've improved by 8x. At the same time, the language models. So we're talking about large language models here, right? So generative AI, the models grow by 1,000x every generation. So we have this fundamental gap between the efficiency of the chips, and so at the chip level, we're at the limits of physics. So it's not going to get more efficient, and we're going to build bigger pieces of silicon to the extent we can in terms of form factor, and then we increase the speed at which we operate them, and that's the only other way we can get faster chips out of. So the models obviously are now at a point where we can get useful utility out of them. So there's a lot of applications that are coming out of it. That wasn't the case several generations ago. The models were not as useful. What that means is that we're probably not going to be training as much, but we'll be now moving to inference. And the concern here is that, how much inference are we going to have, right? Because there's a huge spectrum of applications that are falling out of AI.
So inference means use for those who are not.
Yeah, inference basically means you train the model, you create a model, now you're using it, and that's the future is the growth is basically in the use case of AI, and it's being used basically in a number of ways. Because
that's why you ultimately train in the first place.
Exactly.
To have the use later.
And so that growth basically will be the growth of in terms of covering the population of the planet, and then what are the various number of applications that we can basically come up with, and at what rate will these applications then be using AI? Those are the factors that will lead to growth.
Yeah. If we put this into a data center, right, these chips, then we get to really interesting numbers. And you can maybe speak more about this, but one thing that I saw is that at least a couple of months ago, the largest GPU cluster was the one by Elon Musk in Memphis. It had reportedly 200,000 chips. If you multiply that by the numbers we just talked about, that brings you to, give or take order of magnitude 200 megawatts. Now people are sort of starting to think about building 500 to 700,000 chip clusters, again, with these latest chips that take more than 1,000 watts. So you get to these fabled gigawatt clusters. Is that a realistic projection? And do you think this could go further, or does it stop making sense at some point having that much power, calculation power in one place? Maybe actually, if you could explain to us why it even makes sense to have that in one place and not just distributed all over the world, that could also be useful to understand.
Let's try to dissect these series of questions. First of all, energy is a question of demographics, right? And energy source. So there's a huge confusion in the community, also in the media, about the difference between emissions and energy. Emissions and energy are not related to each other. So the Nordic countries have plenty of energy. Switzerland has a lot of energy. There's very little emissions. So there, we need to worry about the use of energy and where else energy could be used if we don't use it properly. Data centers at the level of gigawatt is not a new thing, right? Data centers have been. I have a satellite image of Microsoft Virginia data center, Boynton, I've been covering in my classes. That satellite image wasn't updated until recently, over 15 years, but you could already see the planned land for it. If you just populate that with super the hyperscaler style racks, which are not very dense, 10 kilowatts, you're already at 300 megawatts, right? So I'm guessing they're probably pushing density a little bit higher. 300 megawatts is the electricity of Zurich. Now, having similar installations for AI, yeah, that's obviously possible. You cannot bring AI into those data centers, by the way. Those racks are 8 to 10 kilowatts. The racks we use in data centers today date back to the telegraph machines. So they're already 100, previous century, beginning of it. And those dimensions can scale up to about 90 kilowatts. You can use the same rack to deliver resources and then remove the heat. Beyond that, you have to go to custom racks. Various companies are building custom racks. Those racks are deeper, higher, and wider. I've seen racks that go to 500 kilowatts now for AI training. AI inference can be done in the same racks. So AI inference, if you have for your large language model 16,000 H100s, which is the latest chip as of last year, you could probably do inference for the same model with 128 A100s, which is the previous generation. So inference takes a lot less computation. And you could bring this together. You bring it together where obviously you have a source of electricity, source of energy, water. But also when it comes to distributed machine learning, which is nodes that are far away from each other, that gets into the topic of distributed learning, which, of course, the farther nodes are from each other, the more constraints there are in how fast you can train.
But so is it correct to say that at the moment, which is the standard approach of training these things, it's good that the machines are close to each other because there's a ton of exchange that has to happen between these machines, and so if they're all in one center, that's just the most efficient way of doing it, as opposed to having them all over the place.
Yeah, in fact, NVIDIA sells you DGX, which are custom design AI training racks, are highly integrated. They come with liquid cooling. They come with NVIDIA's custom fabric. NVIDIA, by the way, charges a lot on their chips, but they charge even more on the network because the network is a monopoly. And because you can buy the chips and integrate them yourself into servers. But yes, absolutely. The thing that gets you with Moore's law slowing down is that you need to integrate more. You need to bring things closer to each other. You need to customize. You need to specialize to offset the negative impact that you would get otherwise. You would get from density. And the next line of innovation in hardware in AI is interconnect. And interconnects in a data center are super cheap technology, not interesting. In a cloud setting, in a data center, services don't really talk to each other. The goal of the data center is to build servers and network and infrastructure as cheap as possible because you want to basically monetize that. In the case of AI, you have to go the other way around. AI training, you have to put in a lot of hardware. It's basically a supercomputing application where you pay for the hardware, but then things get a lot faster and more efficient, so you can create larger AI.
So if we want to build a data center, what will we have to be worrying about? I mean, I guess if you buy GPU chips, that's already your first problem. You need to get the chips. But let's say we have the chips. So then my understanding also, for example, looking at things like Alps in Switzerland, I mean, the obvious thing you have to worry about is where do I get the energy from and how expensive is it? So maybe we can talk about that, right? How do we power these things? And then heating and cooling seem to be important aspects that are not getting enough sort of public scrutiny. Can you help us walk a little bit through?
Yeah. So first of all, Alps is a supercomputer, so that's not a data center.
That's right.
Right. The data centers are infrastructure, utility-style infrastructure we build that are much larger scale than supercomputers. Supercomputers are designed without cost being a concern, because supercomputing is usually subsidized by governments, but it's mostly to allow scientific computing or large computation to advance together, and for that you basically need expensive hardware to make sure you can run these large applications together. Data centers provide cloud services. The servers are super cheap. The network is cheap. Everything is cheap because the goal is to use software to glue everything together and create a massive service at the lowest cost possible. So those two things are a little bit off from each other. Now, we're going to bring AI inference into data centers. So that's going to basically push the cost performance sweet spot a little bit in the data center design. But AI training will always be separate infrastructure, whether it's hosted on the same campus or whether it's its own campuses. In the US, they're building a lot of separate campuses just for AI training. Now, cooling. Yeah. So the goal of the cloud is to build cheap servers. Cheap servers are air-cooled. Air cooling is super cheap. It's not efficient, but it's cheap. AI chips, NVIDIA's chips, need liquid cooling, and liquid cooling is expensive. So
just to double click on that, can you explain why that is? Is simply because they use so much power that that the air wouldn't be physically able to.
So basically, this is actually a really interesting topic because it's a research topic in my lab as well. But basically, you need a certain amount of surface area of your silicon, and that part you need enough dim or dark silicon, which is silicon that's not dissipating a lot of electricity, just so that you can air cool it. So you have a maximum thermal envelope. And that thermal envelope is a function of how much power that surface is consuming and what the area of the surface is, right? So we've been basically, if you look at CPUs that go into the cloud, these CPUs for the past 15 years, they have a lot of dark silicon. Actually, some CPUs we see like Ampere, latest, a couple of one generation old Ampere CPUs, which use ARM processors, they even have unused silicon, so you see gaps in the surface area, and that's mostly because of air cooling. So we've had today's CPUs, the amount of silicon that goes into logic for computation relative to how much memory you have, which is dead, which is dark silicon, doesn't consume a lot of electricity. That's roughly a ratio of 0.5. If you look at Grace Hopper also has CPUs in it, right? The DGX has CPU and GPU integrated close to each other because they talk to each other a lot. Those CPUs have a 2.5 logic to memory ratio. And the reason is that they're liquid cooled. So you move your thermal envelope. If with air cooling, you're basically getting 0.4 watt maximum per square millimeter. You go to liquid cooling, you're increasing that by 3x. You can dissipate a lot more power and a lot more thermal. So you can think of the Grace Hopper CPUs as the Ford F-150 of CPUs as compared to today's CPUs, and which are air-cooled.
Okay.
But air cooling is here to stay. We're just not going anywhere because it's cheap. And so we'll slowly move some of the infrastructure to liquid cooling. AI training is all liquid cooled. That's just basically the GP. They have custom racks they have liquid cooling built into them. And any other GPUs that are used for inference that are integrated into regular cloud servers, those also have liquid cooling, but it's not as tightly integrated as the DGX racks.
Okay. So, because, some of the discussions you sometimes hear is that, perhaps we should build some of these build outs in the future, for example, in the Nordic countries. And I assume that's related to the cooling aspect. So it seems to be a key aspect in the equation, not just sort of a sideshow.
Absolutely. So there's already a moratorium as of a couple of years ago in several countries and several cities on building data centers because of data centers, not even because of AI, they're at the limits of electricity. Singapore has a moratorium. The Netherlands, the entire country has a moratorium, or they're controlling the construction. Ireland announced a moratorium. So this is already happening.
That's because of the energy requirements, not because of the cooling.
Total electricity consumption of the data centers. Yes,
okay.
Not because of cooling. And we'll get to cooling. And in the US, Virginia, I think, is capped, maybe because of the hyperscalers, but also because of government. Texas has its own grid, and they're building like crazy. So now let's talk about cooling. So there is this metric called PUE, which is power usage effectiveness. And this metric finds its roots back to Switzerland, to one of the University of Applied Sciences a couple of decades ago. It tells you about the extra electricity you're using for every kilowatt that you're delivering to your computers, how much more electricity you need to cool it and to deliver the infrastructure, basically. And data centers today, on average, worldwide, they have a PUE of 1.5, which is not very good.
So what does that mean?
So that means that for every kilowatt that you're consuming in computing, you have half a kilowatt that just gets wasted just to keep the computers cool and keep all of the electrical and cooling infrastructure running so that the server can run.
I see.
So it's extra 0.5 kilowatt. Hyperscalers self-declare, they've not been independently measured, but they claim that they're below 1.2. They've been below 1.2 for a while. Co-locators, which are these companies that just build the building, just provide the electricity network and cooling water to the racks, but then they rent rack space to IT customers, and the IT customers basically bring their own servers and host them there. That's a data center market in Europe, the co-locator market. They're on average around 1.4. So they're not as good as hyperscalers, but they're not as bad as your mom and pop data center. We just certified Digital Realty. Digital Realty is one of the top half a dozen multinationals that build data centers around the world. We just certified them in Zurich a few months ago. 100 megawatts data center just outside the airport. It reached a phenomenally high value of, we have a gold, which is less than 1.2. And one of their data centers, two of their data centers are so efficient that we're actually inspired to offer a platinum level for 1.1.
So high efficiency, but in some sense, phenomenally low value.
Low value because the less you waste electricity on cooling electricity, the better it is for whatever energy is left to deliver to the servers. And so that's it. So Nordic countries, they're like Switzerland. They have hydro. They have plenty of source of water also for cooling. They have clean energy, and they're investing. There's a lot of AI that's going in that direction. Today, demographically, still most of the chips are in the US, and there are a lot of chips and custom technology in China. Mm-hmm. Trump just announced that he wants to sell a lot of chips to Saudi Arabia and UAE, but that's where things are. Now, you can go buy the chips, but you cannot bring those servers into your data center. You still need to build proper infrastructure to host these super, super hot chips. Mm-hmm. And that's where we're going with this.
Okay. And let's go back to the energy now after the cooling. So, I mean, that's I think the key concern. This stuff can be amazing, and the AI models that are coming out are incredible. but it uses a lot of energy. And the question on everybody's minds is, where do we get the energy from? And it seems like there are really two questions here. One is, first of all, how do I get the energy in the first place? Because I already have electricity need for many other things. And since we want to fight climate change, we want to electrify everything. So we anyways need a lot more energy. And now these AI people are coming and they also want a lot of electricity. And the second question, which though is often not so much discussed, is what I think you alluded to before. Like, what does that actually mean, right? In terms of emissions later, because you can obviously generate energy in very different ways with very different downstream effects. What are the dynamics here? I mean, you alluded to some of them. Obviously, people are building out renewables as fast as they can. Well, maybe not as fast as they can, but relatively fast. There's this new talk about nuclear. So give us a bit the lay of the land. What's happening?
Well, so first of all, very good question, right? Countries that have issues with energy provisioning, like Germany, they're not going to be building a lot of data centers. Definitely not with a lot of AI, right? That's a huge problem. Countries that have energy, like we talked about Nordics, for now, also Switzerland, they could build more data centers. In the US, the way the current climate is going is that there's going to be probably less regulation. There's going to be less investment in renewables. There'll be more investment in dig-in. AI can help energy extraction, exploration. So that's an opportunity for energy as well. And energy is not really transportable that easily. So it's going to be a local effect. And it's if you have energy, then you can build it. And assuming you can get the chips, if you don't have energy, then you're left out.
Yeah. But so what does that mean? I mean, I think it's interesting to think about that also from a geopolitical angle, though we don't necessarily need to go in the weeds of the politics, but it's nevertheless interesting to see this topic all of a sudden becoming like a key topic, right, in these kinds of discussions. There's this notion that, I think in the past 12, 24 months, I always observed this discussion about, whoever can buy the chips is sort of, ruling the world, so to speak. Now, increasingly, we seem to go into a discussion of like, maybe there will be at some point enough chips, but actually, do you have the energy to run them? And if you don't, or if it's just going to be very expensive the way you produce energy, then there's going to be a price for that, right? And it's not just now for the nerdy scientist here and there, but your entire economy will want to have access to cheap intelligence, and you will basically be able to provision it at the price of your energy. So,
no, you're absolutely right. I mean, I actually think that these two things almost happened at the same time when the news was that each one of the big, most valued companies in the world are investing a lot in AI. And that was when you saw the NVIDIA stocks going up, shooting up. Around the same time, you also heard the news that they're looking for energy.
Yeah.
And there were multiple announcements on that, both in terms of using AI to explore energy, but also partnering with energy companies. If you look at what happened to Texas, there was a gold rush with crypto for over a decade. And that was actually the first customer of GPUs too, before AI. A lot of those crypto farms are now retrofitting into AI training farms. The reason is that they've built them, they have the capacity to cool, but more importantly, they've already bought the electricity. So there is a little bit of that going on as well. But you're absolutely right. It's at the end of the day, it's going to boil down to energy. Who has energy? If you have it and you have the chips, you can go.
Yeah.
And if you look at China has invested a lot in energy, right?
Yeah.
So.
But if people were to ask us, right, so what should any given country do? I mean, obviously, countries can speak for themselves, but I nevertheless sometimes have a hunch that not all countries have maybe understood the full implications of what that would mean. I mean, in a lot of places, there's this notion that we have a set amount of energy. It's almost like a natural law, even though, of course, it isn't. It's just the way we build our energy systems. And we have to go to that level of sufficiency, meaning you have this set amount, and if you want more, you cannot get more. You just need to make your processes more efficient. And that was the narrative, I think, by and large, until AI came along, at least the modern type of AI, as you mentioned, the sort of, LLMs, right, is now 1,000 times more energy intensive than the previous versions. And so I do wonder, right, to what extent one needs to have more open conversations about this, also with the public, right, about what that could potentially mean. I mean, it's a completely legitimate decision, obviously, to say, no, we want to stay at that energy level. You want more AI, figure out a way to make it more efficient, right? I just wonder, can we give good guidance for how this will play out in the future?
I would bring that back to the context of the data center. I would not say that, as a country has to provision electricity for AI. I would say that, of course, AI cannot be hosted by itself. It needs a data center because AI needs data, basically. And so, but if you look at the projections for electricity growth, I think that most governments have expert teams that follow trends, and the trends are they're public trends. Whether the hyperscalers announce their numbers or not, they're basically, there is data you can get from think tanks, and I do believe this 16% growth, which is a lot. It's not. There are not a lot of industrial sectors that have an increase in energy that just comes out of nothing. Usually, when you have growth in energy in one sector, maybe growth in energy in other sectors collapses a bit. Yeah. But in this particular case, there is this growth, and I think that countries are basically mindful of this growth. Now, what you're going to do about it is a good question. On the one hand, as you said yourself, Europe is extremely regulation oriented. And this has also implications for the US and the rest of the world. And on the other hand, we also don't want to miss out, right? So this is it's a very good question.
So maybe just briefly on that, also with the source of energy, what it seems like renewables would be kind of a no-brainer. Then there's now this contentious discussion around, what does that mean for nuclear? I guess at some point in the future, we may be looking at fusion, but I think that's too far out for people to really integrate that into their current calculus. Whereas nuclear, of course, you can in principle build. There's this question of, do the newer reactors make sense? You alluded to that before. But then, of course, there's also the simple ugly side of things, that some of this demand is just going to be taken care of by fossil fuels. Is there any data on what that ratio is, or do you have any visibility?
Yeah, I'm not an expert on this topic. I follow it just like yourself. Okay. It's clear that Middle East, UAE, Saudi Arabia, they're putting a lot of money behind this. The UAE, actually, Abu Dhabi is the richest of all of them. They've just decided that they want to take an entire sovereign fund, and that should fund the entire AI ecosystem, including data centers, including operators, including companies that create AI, and including their university, which they've built. And they're basically going to use fossil fuel to pay for it. And you can also imagine that Abu Dhabi would not be the best place to host data centers. So they're not going to be as efficient. If you reach a PUE of 1.4 in Abu Dhabi, that's actually a super efficient data center because it's very difficult under those temperatures. Modular nuclear, like I said, is 10 megawatt, from what I understand. So that's peanuts. Like the 100 megawatt data center we certified in Zurich, there will be 10 modules. There wouldn't even space for that. Building nuclear plants takes a long time. So there's no question of, okay, we're going to build now and tomorrow we'll have it. So that's another issue. Renewables are good, but again, it's related to the source of energy and what your capacity would be. Yeah. So I think from that perspective, just there is energy apartheid, and because of that, there will also be AI apartheid.
Yeah. So what can we do about this actually? So, I mean, this is all potentially a little gloomy, but of course we are researchers, right? We try to fix things here. Two broad ideas that come to mind are, on the one hand, we can obviously try to do things more efficiently, right? And the other side, which I think is also not often enough talked about, is, well, we're not just creating this technology because we're geeks and we like just to create tech, but actually this technology could be used to make other parts of the system more energy efficient. That was the key argument of Urs Hölzle, right? When I had him on, he basically said, oh, look, I mean, sure, we can optimize this world of electrons over here, but really we should use it to then fix the world of atoms, moving atoms around, meaning for heat and for transportation. So can you give us a bit, you're looking in particular, I'd like to have your view on where we stand with like more efficient chip designs. What do you think we can do with more efficient algorithms? Is that an area that has some important gains ahead?
So yeah, that's a very good question. Now, given post-Moore, so Moore is basically coming to an end, and there are ways to get the silicon a bit more denser. We can build chips in the third dimension that just gives us a one-shot improvement. It's not exponential. There are future crazy technologies where you can even integrate chips at a much finer granularity, where individual computing elements can be built in 3 dimensions, and people are talking about that. We'll have a keynote lecture at the annual event for EcoCloud this year that will talk about that from Stanford. There are ways to do this. That's super expensive, not clear when we'll have that. Then there is, of course, designing the chips differently. NVIDIA is not the best, most efficient way of computing AI, because NVIDIA creates GPUs, and GPUs are graphics processing units. They're not related to AI. We can make AI processing units like the ones Google makes. That gives you another order of magnitude, but that's a one-shot improvement. That's it. And then we can talk about algorithms, and we can talk about other forms of efficiency. Today's GPUs are not fully utilized. Microsoft had a paper in the software engineering conference last year where they measured the utilization of GPUs in deployed environments, and they say that 50% of the time GPUs are idle. That gives you another factor of 2 improvement. So you have these orders of magnitude improvement. Now you go to algorithms, you have a 10 to the power of X question mark improvement. What can you get out of that? Well, it's the way we built AI today is the way we built pickup trucks in the US, which is the most common form of car sold is a Ford F-150, which is a ginormous pickup truck. That's not the best mode of transportation, but people like it because you could do whatever you want with it and put stuff in it when you're traveling. That's how we're building AI today. There are much more efficient ways of building AIs, and I'm sure we'll get there. And I think EPFL has a wonderful AI center and a collection of faculty and top researchers working on this problem. So I am hopeful. AI can also improve a lot of processes in industry that makes things more efficient. That would also lead to less use of resources in other sectors and other segments of society. So there's already clear examples of that. And there's no question about it. I'm pretty sure that we will also have those benefits. The most important thing is that we need to measure to know how much electricity, how much resource we're spending. I think this actually comes from Kelvin. There's a quote from Kelvin: "Is to measure is to know." And that's the challenge today in industry, to make sure that can we properly measure exactly what we're putting into data centers and what the output of that is.
Yeah, and then I think I would maybe double down on that on the other side of the equation, right? That we somehow also measure how much energy we can save in other processes. Yeah. So we can then present the bill and say, look, this is actually net positive, right? Or net negative, I mean, depending on how you look at it.
Yeah, and absolutely. And by the way, on the measurement, I'd like to put in also a shameless plug that SDA, we're a nonprofit. We have 3 calculators. So we help data center operators properly measure, quantify their efficiency in a data center, energy flows in the IT stack, and also the emissions from the source of electricity. But there are other initiatives that are related to AI. For example, Hugging Face has an Energy Star initiative where they classify the energy requirements of AI from an application perspective, because not all applications need the same size AI. And so if you properly use the right models for the right application, you can also get orders of magnitude difference in resource requirements.
All right. Good. So to wrap this up, what could we sort of propose to people who are concerned about this, right? I mean, I just realized that very often one of the main concerns, again, as I mentioned in the beginning, out there is the energy need of AI. I think mostly people do not deny the benefits of that AI can bring, but they are looking at the energy requirements with a certain concern. And we sort of looked at different angles now, how this could play out. Like, what sort of advice would you give to people who think about this? Because one of the common advices that seems to be out there is just use it less, right? You're using ChatGPT, that means almost you're a bad person because you're spending that much energy, right? Sometimes you even see that on social media. Somebody creates, a funny image or a funny video with AI, and then there's comments underneath saying, did you really need to spend all that energy? Which I always find a bit weird. I mean, just thinking that they may have just driven their car, their gas-fueled car 30 kilometers to the office just to scold someone on using a few watts. What would you say is the best way to sort of think about this, where this is heading, and what one could do individually, but perhaps also from a policy perspective?
I mean, it's a very good question, right? And I've thought about it a little bit. I would say, you could do your own back of the envelope calculations, and you would probably come to the same conclusion that just, interacting with ChatGPT has its limits on a per day use case basis, and you're not gonna cause huge problems in the energy markets because of that. However, what we don't know is every interaction you have with these IT platforms, how much AI is going on in the background. Those are probably bigger concerns because there's absolutely no transparency into what the hyperscalers are doing. So I would say, are you using AI to entertain yourself? You can probably control that a little bit. If you're using AI to be productive, I'm not too worried about that right now, right? Based on just a person by person's use case on a daily basis, right? What is happening in the background? I have no idea. If you control your use of IT services in general, you're probably helping a little bit. But if you absolutely want to use it for your productivity, I would not limit myself today.
Mm-hmm. Okay, because it's you saying on a per use case, it's really that's probably not where
I wouldn't worry
where the
too
big
much
effects
about
are.
it. If you go and ask AI for entertainment, just give me a 10-minute video of something. Well, that's a video you're going to throw away, and that's there are projections from MIT Technology Review that say that a 5-minute video is already a kilowatt hour of energy. That's a lot of energy.
That starts to add up. Yeah. I mean, that's in general. I find that quite interesting. That separation between entertainment and use, because if you use it in a text form, mostly it's really for concrete use. Yeah. I mean, not to downplay that you may have very legitimate use cases for video and so on. Yeah. But it is, I think people do underestimate the amount of energy that goes into the production of some of these videos. Yeah. As fascinating as they are. Okay, good. And so if people want to learn more about these topics, where would you direct them to? Especially also, EcoCloud has its own website. The association has its website.
Yeah, association's website. We write a lot of blogs. We, for those of us who are professionally connected on LinkedIn, there's a lot of blogs. We write. Also, SDA has an insight that we have newsletters. We publish on LinkedIn. There are, MIT Technology Review, like I said, they just have a series of articles that are coming out. In my academic community, the ACM, Special Interest Group in Architecture, SIGARCH, we have a blog, and I'm actually writing a series of articles there in the coming weeks. So there's plenty of credible sources available.
All right.
And it also read from multiple sources and make sure they match, right? Yeah. They're not off, right?
Yeah. Exactly. Good. And we'll link to some of those sources that you mentioned in the notes. Good. All right. Thanks so much for coming.
Yeah. Thank you for having me. Great conversation.